is very rapid and energy efficient pre-cooling method. Vacuum is created pressure is decreased below atmospheric pressure, iceberg, and some meat products. Vacuum cooling system has three main components: vacuum chamber, vacuum pump, and control.
Yine söylediğim gibi bu konudaki bizi çalışmaya iten ana etken işte yerlik bir takım Türkçe kitaplarda bu konuda. Bir de çok fazla kitabımız maalesef yok. Yani soğutma klima alanında çalışmak gidecek kaynak eksikliğimiz var. Yine bir havalandırmada bu çıkış cihazları ne iş yapar? Hava düsturuz yani şeyi oluşturarak, karışımı oluşturarak mimari dizayna uygun olması gerekiyor. Yani genel var ve bunların işte belli noktalarda özellikle iç hava dağılımı ile ilgili bir takım işte kavramlar, özellikle hava soğuk hava yazın soğuk gönderiyorsak havada yoğunluk farkından dolayı aşağıya doğru bir düşme etkisi önem kazanıyor. İnsanların yaşam alanı, occupied zone diye ifade edilen konfor bölgesi tanımı, canının genişlemesi, yayılması, serbest jetle ortam.
Time period needed for the surface soil temperature to reach TM. Obviously, surface soil temperature to reach ambient air temperature is even for Izmir. In addition, gamma is the most important value, is the damping depth, and was determined as was applied to depths from 5 to 300 June. A 1 year period had been taken in hours and
2011 to 2015. Natural gas, it's very, very small, and also water heaters, very, very small, and boilers, water heaters, etc. These cases can be ventilating of.
My presentation into three parts. Firstly, I will start a brief introduction. After that, I am talking about methods. Methods include vision mixture. Başaran and Özgener also investigate the effect of geothermal binary power plants. McCall and his friend made extra topology.
Show that the coating of a hollow brick wall with a phase change material improves thermal comfort and increases the maximum wall temperature by 4 degrees Celsius.
But we will discuss about the system selection and duct design. The most of the edition is previous year, and the objective was clear. We have to well-working carpentry shop and welding shop. Of course, there are some competitive patterns that we were supposed to meet.
Today we start our program with invited speakers session number 5. And our chairman will be Professor Dr. Eckert A. Grohl from Purdue University, Director of the Office of Professional Practices. I'm glad to introduce you Professor Dr. Eckert A. Grohl.
Is this on? Yeah, okay, good, thanks. Good morning, everyone. I also like to welcome you to this Inviter Speakers session number 5 this morning. I think we have 3 great presentations. And without further ado, I will introduce our first speaker this morning. And that is, let me make sure I have all this information here. This is Professor Sherif, Ahmed Sherif. He's a professor of mechanical and aerospace engineering at the University of Florida. He's also the founding director of the Wayne and Lila Mazur HVAC laboratory. I hope I pronounced that right. With the sponsors and the endowments, it's always tricky to make sure that you have the right names. He's also the director of the Industrial and Assessment Center, all of this at the University of Florida. In addition, he is a fellow of ASME, he is a fellow of ESHRE, he has received numerous awards for his research, for his professional activities, including some paper awards. I've known him for quite some while through our service on the U.S. National Committee for the IIR. We meet regularly at ESHRE. It's a nice collaboration. I very much enjoy the interactions. Over the years, he has published over 400 papers, quite an accomplishment. So I'm really looking forward to his presentation today. And his presentation will be Absorption Refrigeration Technology, Past, Present, and Future. Please help me welcoming Professor Sherif.
Good morning. Thank you very much for the nice introduction. I appreciate that. And it's always my pleasure to be here with my friends. I would like to talk to you today about absorption refrigeration technology and give you what I would like to call past, present, and future. The future part is going to be my prediction of what I think the future would be. So it's not based on any scientific facts, but it's based on educated guesses on my part. The work that I'm going to show you today is predominantly work that I have done in my own research group. Absorption refrigeration is so vast that it was going to be a challenge for me to incorporate a lot of things that are going on. But I'm going to show you some of the basic ideas, and then we'll go from there. So with this, I would like to move to the next slide. This is the outline of my presentation. I will give you a brief introduction to absorption refrigeration technology. Then I'm going to give you a couple of quick slides defining some thermodynamic performance terms and also some thermoeconomic performance terms that would be important in terms of the cost issues. I hope I'm not talking too fast for the translator. I did that before, so I apologize if I'm a little too fast. Then we're going to talk about the classification of absorption machines. And I'm going to give you some detailed description of some of the performance of single, double, and triple effect absorption chillers in particular. As you will see, there are absorption chillers, absorption heat pumps, and absorption heat transformers, as I will discuss the details of those. I'm going to focus more on the absorption chillers part of it. If you want more details on the others, take my card and contact me, and I'll send you copies of the papers that we have written. I have about seven papers that we published, mostly in ESHRE, and I can give you more details about the calculations we did. Then I'm going to also give you some of the thermoeconomic data that we've developed in terms of cost and life cycle cost and so forth. Finally, I will give you a prediction of what I think absorption, or the role that absorption is going to play in the future. Okay, some basic thermodynamic performance definitions. These are the terms that I will talk about quite a bit here today. The coefficient of performance, all of you know what that is essentially what you gain divided by what you pay for. So in the particular case of an absorption chiller, you will see that what you gain is the cooling effect or the refrigeration capacity, QE or Q dot E, and then what you pay for is the heat added into the generator or the boiler, what sometimes they call the boiler. And of course, we ignore the pump work in this particular equation. Then the second law, efficiency, or sometimes referred to as the ratio between, and that's the very last line, that's the ratio between the coefficient of performance of a given system divided by the coefficient of performance of a Carnot system operating at the same temperature level. Then there's the exergetic efficiency, the exergetic efficiency is defined as the useful exergy divided by the supplied exergy. So the exergy is the available energy. So when you have the supplied exergy becomes your reference point, and what you produce in terms of useful exergy is divided by the supplied exergy, which gives you some ratio, and you can make that a percentage if you want. And the flow, the exergy of a given flow is given by the equation that has epsilon, which has the enthalpy difference between what you have and a reference enthalpy, and then the T0, or the reference temperature, mostly the ambient temperature, times the temperature, the difference between the entropy and the entropy at that reference state. There are two terms that I would like to focus on. In thermoeconomics, this is a huge subject, and there are many people that have done work, Professor George Tsacharonas at the Technical University in Berlin, and others who have done a lot of work on that. But there are two terms that I would like to define, because you will see some of the data here on those. One is the capital cost ratio, and then the other one is the exergy cost ratio. Thermoeconomics is basically a discipline that combines both thermodynamic and economic analysis for thermal systems. And its main objective is basically to minimize the product cost for a given thermal system for a given capacity, or to maximize the product capacity for a given total cost. One of these two things. Either to minimize the product cost for a given capacity, or maximize the capacity for a given total cost. The two terms that I would like to discuss with you would be the capital cost ratio, and that is defined as the ratio between the capital cost of the absorption chiller divided by the capital cost of a corresponding vapor compression chiller. So if the two are equal, then they give you a capital cost ratio of 1. So we're going to make comparisons with vapor compression refrigeration systems. And the other one is called the exergy cost ratio, and that is the ratio between the primary thermal energy, exergy, divided by the electrical energy, which is, of course, is a reference for that exergy. And if you have a free waste heat source, in this particular case, the exergy cost ratio would be 0. Okay, so those are the two definitions that I wanted to share with you. Now, let's go back to absorption machines in general. Absorption machines can be classified in many ways, but I selected two metrics for you today. One is the classification based on the final output, or the product that you're looking for. That, and it would either be cooling, or chillers for cooling applications, or heat pumps for heating and cooling applications, or what they call absorption heat transformers. And I'm going to tell you a little bit more about the absorption heat transformers in just a minute. You could also classify them based on the working fluid, and the two most common ones are the lithium bromide water working fluid, or the ammonia water working fluid. And then, of course, there are many other absorption pairs that you can find that are less common. Those of you who are familiar with some of the research would attest to that. Let me just spend a minute on absorption heat transformers, because that is a term that is less common for many of us. They basically are typically used for recovering waste heat and upgrading that waste heat to higher temperatures. Sort of like a temperature booster, if you like. Now, you know that the temperature is sort of a measure of how high the grade of energy is. So the higher the grade, the higher the temperature, the higher the grade of energy as far as thermal heat, or thermal energy, or heat energy. And of course, and work is one of the highest, or the highest form of energy, higher grade form of energy, and then followed by thermal energy. And thermal energy is classified based on how high the temperature actually is. So you want to boost the temperature level. That means that you're going to upgrade the energy level. The absorption systems for heat transformers basically are used as temperature boosting applications or temperature boosting applications, and they can use part of the waste heat to power themselves for that, and that's one of the advantages that they have. These now can be single, double, or triple stage, and just for the sake of whatever that may mean, they use triple stage, double stage, and single stage for absorption heat transformers, and they use triple effect, double effect, and single effect for absorption chillers. I don't have the rationale for that, but that's historically what they use. The term, you shouldn't say double stage chiller. You should say double effect chiller and then double stage heat transformer. They're very popular in Europe and Japan and the United States, and as I said, they're known as temperature boosters. Now, absorption chillers is the other category that I would like to discuss, and I'm going to spend a little bit more time on that. I'm going to skip the part on absorption heat pumps because most of you know what heat pumps are, and there's no point in making the presentation any longer than it has to be. So these are basically heat-operated machines. These heat-operated machines, they employ the available waste heat, idealistically speaking, the available waste heat from power plants and from industrial processes as their driving source of energy. And the idea is to produce chilled water for building cooling applications, and therefore you improve the overall energy utilization in the process. Of course, the vapor compression machines are more efficient. Their coefficient of performance is much higher, but they do use a very high form of a high-grade form of energy, which is electricity. And you know how electricity is generated? It's generated by most of the time by burning fuel, utilizing the thermal energy from that in a power plant, and then transmitting the electricity over transmission lines, having losses. The power plant efficiency is somewhere in the vicinity of 36% or 40% or something in the vicinity of that. Then you have about 15% losses in the transmission lines, and then you get the electricity on the other end and the end user. And when you use it in a vapor compression machine, you have to really incorporate all the losses in the process. And then they have historically also been associated with greenhouse global warming problems and ozone depletion problems, as many of you know. So the application of absorption chillers is one effective way to reduce peak demand for air conditioning usage. Most of the currently residential and commercial absorption chillers in the market employ either single effect or double effect. The triple effect are less common than the single or double effect. The single effect is limited by the ability to utilize high temperature heat sources. So we're looking at 70 degrees to 100 degrees for a single effect chiller to operate. And some of the references I cited here, Perez Blanco and Grossman in 1981, and Issa and Holland in 1986 is a good classic reference. Now the double effect system is in fact the one that is most common. It represents a significant improvement over the basic single effect system. And again, some of the papers here that you could look up, Alfeld and Radermacher from Maryland, they have several double effect cycles that they proposed. And in fact, there is a book where Professor Radermacher had a whole book on absorption machines that you may be interested in. Many other references here that you see, and there is a last reference by Ludovici and Worek that I got a couple of days ago from my friend down here who has done some work with one of his students on vapor recompression absorber. And if you have any interest in that, you can talk to Professor Worek. He's sitting on the front. He can give you more details on that. This is a single effect absorption chiller, and I'm not going to spend any time walking you through the cycle. You know that if you look at the left side of the cycle, you will have the condenser and the evaporator, and then on the right side of the cycle, you have the generator, the absorber, the heat exchanger, and the solution pump. And actually, the way I teach this to my students is if you can draw a line, a vertical line here, you will see that the left-hand side is exactly the same as the vapor compression cycle, except that it doesn't have a compressor. And if you look at the right side, you will see that you have the part that has a solution. That's the solution in it. Of course, this is where the heat is added in the generator, and this is the absorber. Here, a heat exchanger is in typical, and then the solution pump. You take the solution from the absorber, pump it back into the generator. And the idea is if you're using lithium bromide water system, it gets to be a little confusing when you use lithium bromide water versus ammonia water. If you're using lithium bromide water, the strong solution leaves the generator because when you heat the generator, the water vaporizes, and the remaining lithium bromide solid remains, so you have more concentration in the bottom of the generator here. The opposite is true in the absorber. When you have water vapor coming from the evaporator and then it condenses by removing heat, you remove heat from the absorber, so you condense the water, and as a consequence, you have less concentration in the absorber. Now, that exact scenario, the exact opposite scenario happens in the lithium in an ammonia water system because the absorbent in the lithium bromide system is so the absorbent is the lithium bromide and the refrigerant is the water. In the ammonia water, the absorbent is the water. The absorbent is the water, and the refrigerant is the ammonia. Okay, it's sort of, the water plays a dual role. It's a refrigerant in the case of a lithium bromide water system, and it's the absorbent in the case of the ammonia water system. And basically, the way you know that, you just see what goes into the evaporator, and that becomes your refrigerant, and then the other one becomes your absorbent. That's a double effect absorption chiller, and you can see the During diagram here at the bottom showing the pressure, temperature, and concentration as well, and I hope you're partially familiar with that. This is a triple effect absorption chiller. And again, I'm going to zap through those very quickly. I'm going to show you some of the performance metrics. And the performance metrics, thermodynamically speaking, I have categorized them in terms of the coefficient of performance, the second law efficiency, and the exergetic efficiency. The second law efficiency, or sometimes they refer to it as the thermodynamic efficiency. Again, it's the COP divided by the Carnot COP. Now, you see here the comparison is between a single effect, double effect, and triple effect. And I'm showing you the Carnot cycle as well. Of course, the Carnot cycle is an unrealistic cycle, so you can see it on the left side, on the top left side of the diagram. Now, it's shown for two different cooling water temperatures. The cooling water is what goes into the condenser, and the cooling water is another way of saying how high the condenser temperature actually is. The higher the condenser temperature, as I'm sure many of you know, the higher the condenser temperature, the less efficient the refrigeration machine actually is. And the lower the evaporator temperature, the less efficient the refrigeration machine actually is. So the refrigeration machine is less efficient at lower evaporator temperature and higher condensing temperature. Less efficient as in lower COP. But of course, at lower temperatures for the evaporator, the quality of cooling is higher. The quality of cooling is higher as in you get lower temperature cooling, which is a good thing. But you get it at a lower efficiency. So I always like to say, when someone tries to sell you a chiller and say the coefficient of performance of the chiller is X, Y, and Z, give you a number, make sure you ask at what temperature. Because if he comes and says, I'm going to sell you a chiller that has a coefficient of performance of 10, doesn't mean anything. I can sell you a chiller that has a coefficient of performance of 1,000 if I wanted to, but it's not going to do anything. It's going to cool maybe by 1 degree or something like that. But what you want is you want to get a low temperature cooling with a high COP, not just a high COP. This is the thermodynamic efficiency, and you can see for the single, double, and triple effect, again, you see something that is common, which is a peak. You see a peak. See here, you see a peak, and you see a more profound peak in the second law efficiency, which is the ratio between the COP and the COP Carnot. And that's very important because you would want to know exactly where you would maximize the COP for the given system relative to the Carnot COP. And this is the exergetic efficiency for those of you who are into exergy, such as my professor, my dear friend Professor Kilkish, would probably be more appreciative of that, because I believe, and many of that community believe, that eventually over time we will be paying not for the cost of energy, but we will be paying for the cost of available energy. I think over time that is going to be the trend, as opposed to the cost of energy. So exergy becomes an important issue to deal with. And that's what the people that do thermoeconomics will tell you. This is the, now I have to say that I showed you that the performance data previously in terms of the cooling water temperature. Now I'm going to show you the same performance data in terms of the chilled water temperature, which is the evaporator side of the equation. And you would see that the same trend, you got more or less the same trend. Of course, here in this case, the lower the evaporator temperature, the lower the COP, as opposed to the other way around with the cooling water temperature. And this is the thermodynamic efficiency as we defined it, the COP divided by the COP Carnot. And this is the exergetic efficiency. And you can see that there is a profound peak for the exergetic efficiency in the case of the chillers, the single, double, and triple effect. Now I'm going to take the double effect chiller in particular, and I'm going to dig more into it and show you that there are several types of the double effect chiller. I have selected several of those types, and we've done some investigation on their performance. And I'm going to show you first what they look like, and then I'm going to show you what their data look like. So there are basically the so-called parallel flow double effect absorption chiller. And let me fast forward here to show you what it looks like. This is a parallel flow double effect absorption chiller. And for this particular one, it has basically three pressure levels, a high pressure level and a medium pressure level and a low pressure level. And this design can improve the energy efficiency and reduce the risk of crystallization for the lithium bromide water solution in the cycle. The crystallization, of course, is a serious issue with lithium bromide, because lithium bromide is solid. It's like salt, essentially. And if you have solid forming inside the loop where the working fluid is, then you've got a problem. The solution pump will have problems pumping a mixture of solid and liquid. So that you'd avoid crystallization. Crystallization would be more likely at lower temperatures and at higher concentrations. So if the concentration is high, you have more likelihood of crystallization. If the temperature is low, you have more likelihood of crystallization. If you have both of them, you have a very high likelihood of crystallization. The heat rejected from the high temperature condenser is introduced into the low temperature generator to generate additional water vapor from the weak solution. In other words, milk the cow more. And nearly 70% more water vapor is generated without extra heat input, and that of course results in higher efficiency or higher COP. So this is the double effect. Now there is another type called the series flow type, the series flow double effect absorption chiller. And in the series flow double effect absorption chiller, you have two possibilities. One possibility is to have, and let me just show you what it looks like first. The top one shows the solution to high stage generator going first, and then the second case shows the solution to the low stage generator going first. So if you go for the first case, the weak solution is delivered to the high temperature generator first after it leaves the absorber. And then in the other arrangement, the weak solution enters the low temperature generator first and then enters the high temperature generator. Unfortunately, both of these circulation schemes experience high risk of crystallization in the lithium bromide before the strong solution returns to the absorber. And the reason for that is because of the high concentration and low temperature combined at the same time. So you have to be very careful about that particular design. Then the third and last type is the so-called dual loop flow double effect absorption chiller. And that's what it looks like here. That's the dual loop flow double effect absorption chiller. That has a bit of an advantage in the following sense. First of all, you have basically two individual single effect absorption cycles are cascaded together. The two individual single effect cycles are cascaded and operated together as a dual loop double effect chiller. So in this case, the high temperature heat source is employed in the generator of the high stage loop, and that generates water vapor from the lithium bromide water solution. And then the heat rejected from the condenser of the high stage cycle is recovered and introduced into the generator of the low stage cycle. I have a suspicion I'm making the life of the translator very difficult, so I just had that thought, so I do apologize again if I'm a bit too fast for the translator. Let me know if the translator is giving the message. If not, please let me know, all right? Okay, there's an advantage in the case of the dual loop flow double effect absorption chiller in that the system can employ different working fluid pairs. So you could use lithium bromide in one loop and ammonia water in another loop as an example. So that gives you more flexibility and more freedom. And some designers have actually selected other pairs that are outside the two most common ones. Let me show you some of the data for the performance data for those three types of double effect absorption chillers. Kind of digging deep into them. So here I have the COP, again the COP, the second law efficiency, and the exergetic efficiency. You see the single effect and the double effect. Of course, we're using the single effect as a reference frame to compare things to. So you can see the double effect for the parallel flow, and then for the series flow type number 1 and the series flow type number 2, and then for the dual loop flow, you can see that the double effect for the parallel flow has a good COP relative to the others. You've got the dual loop also has a higher COP. The series 1 and the series 2, or the series type 1 and the series type 2 are in the lower end of the things. So that's for the COP. And then for the second law efficiency, the ratio between the COP to the COP Carnot, you've got that trend for the 4 types of the double effect. And then for the exergetic efficiency, you get that performance again for the 4 cases of the double effect absorption chiller. Now, all of those have been shown to you in terms of the condenser temperature. We've used a condenser temperature of 29.4 degrees C. What I'm going to show you now, I'm going to show you the same thing for a 35 degrees C condenser temperature, which is going to give you lower values for the COP and for the second law efficiency and for the exergetic efficiency, because of the fact that now you are operating at a higher, at a warmer climate, essentially. In a warmer climate, you will have lower efficiency. And that's the second law efficiency for the higher end, the higher temperature, the 35 degree temperature, and then that is the exergetic efficiency. Again, all of the 4 types are shown in this case, and of course you see the single effect by itself. Now you see the single effect is operating in a lower end for the heat source temperature. It's not really good for, the single effect can't handle higher heat source temperature. This is where the fuel or the source of heat is. So here you're talking about somewhere between 110 to 160, 170 degrees for the range of operation for the double effect system. Now, I'm going to switch the topic now to thermoeconomic performance. And the thermoeconomic performance, I have several parameters to show you. One is the so-called specific life cycle cost. The specific life cycle cost, which is defined by the value of the dollars or the cost divided by the kilowatt hour. So dollars per kilowatt hour. And you can see the single and double and triple effect versus the vapor compression. So we use the vapor compression machine as a reference frame. And you look at the single effect, of course, in the lower temperature range for the heat source, and the double effect in the middle temperature range, and of course the triple effect in the very high temperature range. If you have a nice high-grade energy source, like in the 200 or 180 degrees and above, you're looking at a triple effect. You would want to use a triple effect in this case. And you can see that there are places where the vapor compression cost is lower, and there are places where the vapor compression cost is higher. So you need to sort of work your way, walk on eggshells, and kind of work your way through that tunnel, I suppose. Now, this is the specific life cycle cost as a function of the number of years of operation. And the number of years of operation, as you work your way towards 15, 20, 25, 30 years, your specific life cycle cost, of course, comes down. And you can see how the single, double effect and triple effect versus the vapor compression compare. We're talking here for a system that has a cooling capacity of about 500 tons and an equivalent full load hours of about 3,000 hours. Of course, all of the data will change. This is the interest rate here that we used was 8%. You have to, and if you need the equations to be able to compute that for any other cases, please let me know. Again, the paper is available in the open literature. This is another scenario showing the same thing, but as a function of the equivalent full load hours. And you can see that as the equivalent full load hours increase, again, the specific life cycle cost goes down. This one, the vertical axis is the specific life cycle cost. Again, I apologize for the illegible vertical axis, but the capital cost, this is what they call the specific life cycle cost as a function of the capital cost ratio. Capital cost ratio would be, again, the ratio between the cost of the capital, or the capital cost for the absorption system versus the capital cost of the vapor compression system. So the capital cost ratio of 1 means that the two have the same exact cost. Capital cost ratio of 2 means that the absorption system has twice the capital cost of the vapor compression system. And this also shows the specific life cycle cost as a function of the exergy cost ratio. The exergy cost ratio, again, is, as we defined it before, is the ratio between the exergy cost of the fuel versus the exergy cost of electricity, in this particular case as a reference frame. If you're using a waste heat source that's free, then the exergy cost ratio is equal to 0. So this is my last slide, the future of absorption refrigeration. Where do we go from here? I predict that absorption refrigeration is going to become more and more relevant than ever before. The reason is that we are at a point in our lives where we have the efficiency has increased so high in many of the machines that we use. The vapor compression machine is an excellent example where it really is a very, very, very efficient machine, and any improvements to that machine is becoming very difficult. I know that a few years ago, and I guess Professor Grohl has had a project for the Air Force Research Lab, if I'm not mistaken, where he looked into vane expanders, rotary vane expanders, I think it was, and they were basically trying to replace the expansion valve with an expanding machine, an expander, in order to get some recovery or work recovery. You had something called EDWOW, which is the output devices. Let's see, what was it? I forgot. The acronym was EDWOW, or something was output work. Okay, so this is how desperate we have become. Is we're trying to get anything and everything out of the vapor compression machine because it's very efficient. So my prediction is that because of our interest in milking the cow or squeezing the lemon to the last drop, we are going to get to a point in our lives where we're going to look into recovering some of the waste energy, and heat-operated machines are the way to go with that. So already you see that the term CHP and CCHP, you've heard these terms, the combined heat and power, and combined cooling, heating, and power, and distributed generation. Many of you have heard that term, distributed power. I know in Lebanon during the Civil War, they had, because there was the power plants were bombed out, and they basically had to, everybody had to generate their own electricity in their own backyard. And they were selling electricity to their neighbors. And necessity is the mother of invention. So if you generate your own electricity on site, you become totally self-sufficient. And that seems to be the way we're heading. The so-called there are micro turbines now. You could have distributed generation for your subdivision and things like that. You live in an apartment complex, and you could actually become independent of the grid, and you can sell your excess electricity to the grid, and then the grid will get you some of that back if you need it. So there is a little bit of that going on, and I think absorption is going to play a role. And just to prove that, we have at the University of Florida a working tri-generation system with water production, and that we have a 100 horsepower gas turbine engine working with a 20 horsepower absorption machine in our lab at the Energy Research and Education Park at the University of Florida. And the water production comes actually out of the condensation of the exhaust gases. There's enough moisture in the exhaust gases that you could condense the water out of it, and you produce about 1.3 gallons of water for every gallon of liquid fuel you burn. Of course, you have to purify the water at the end because it has sulfur and all that. But eventually, you could have a system like that in the desert. And actually, the Army has funded some of that work. The U.S. Army has funded some of that work because that system you can deploy into the desert in the field where you have the operation or the military operation, and then you can put it back on the C-130 transport plane and put it back and remove it from one point to the other. So there is that portability and the ability to move around. Anyways, I hope I didn't take more than my allotted time. Thank you for your patience, and it's my pleasure to be here again with you. Thank you very much.
Thank you very much, Professor Sherif. Great presentations. We have 45 minutes for each presentation slotted. We started about 15 minutes late, so we're going to take to 1:15 roughly to complete the session. So with that said, we have some time for questions. Does anybody have a question for Professor Sherif? Yes, please use the microphone and state your name and affiliation.
What do you think about future?
Please state your name and affiliation.
I'm Veysel Ergül, and I want to ask a question about what do you think about future of direct gas-fired absorption heat pumps for heating purposes?
What do I think about the future of absorption heat pumps for heating purposes? I actually have done work in that field. I didn't show it today, but we have looked into that, and I can probably give you a copy of the paper that would give you more details. Of course, in the practicality of things, it's not, I don't foresee an immediate application to it, because if you're talking about residential, in the residential market, I do not foresee a future. or at least not in the foreseeable future. In the commercial market, there is a possibility, but not anytime soon. Although I've seen some commercial buildings use absorption, but it's not as common as in the refrigeration application part of things. You're more likely to see that in food stores and in distribution centers and all that, as opposed to food distribution centers, as opposed to air conditioning applications.
Yes, please go ahead.
Yunus Çengel, Adnan Menderes University. I'm just curious about the adsorption cooling as opposed to absorption chilling. What is your assessment of that?
Done no work in adsorption, refrigeration, or cooling whatsoever. I know just as much as you do. So, and I've learned when I don't know the answer, I should say I do not know the answer. In the classroom, I generate another question and I answer that, but not for you. So,
Zeki Yılmazoğlu from Gazi University, and I would like to know about the reverse parallel flow type absorption chillers. What do you think about them? Reverse parallel flow type.
I didn't get the first word. Can you say it one more time?
I would like to know about the reverse parallel flow type absorption chillers. Reverse parallel flow type.
Reverse what?
Parallel flow.
Reverse parallel flow. What specifically do you want to know about them?
Coefficient of performance when you compare the series flow or parallel flow type.
I do not have the data off the top of my head, but I can dig it up for you. I do not have the data off the top of my head. I'm sorry for that.
Okay. Professor Sherif, thank you very much one more time for giving a presentation. I have a little present here for you. Okay, with that, we're coming to our second presenter. It's my great pleasure to introduce to you Professor William M. Worek. He's a professor of mechanical engineering at Texas A&M University. He's also the executive director of the Eagle Ford Center for Research, Education, and Outreach. He has spent most of his career at the University of Illinois in Chicago, where he actually moved up to the rank of department head for about, and I think he led the department for 10 years or something like that. Was also the director of the Energy Resource Center there. Professor Worek has been working on desiccants for over 35 years, development new materials and doing analysis and all kinds of work in that area. He's very active in ESHRE as well, where I've met him on the technical committee for desiccant and other technologies that are close to his heart. So with that, it's my great pleasure to introduce Professor Worek, and please help me welcoming here for his presentation. His presentation, I should have mentioned that, his presentation is now the continuation. We just heard absorption, past, present, and future. Now we're hearing desiccant, past, present, and future developments. So, thank you.
Thank you, Eckert. And maybe I can answer the absorption question after the end of my talk. So keep that in mind. Today what I'd like to do, I didn't give an outline in my presentation, but I will present basically open cycle adsorption, give you some things that happen, some rules of thumb, look at new developments. I'll look at closed cycle adsorption. I'll also look at absorption, open cycle, and then some new things that are happening in closed cycle absorption. So that's sort of a rough outline of my presentation today. So why are we here? The reason we're here is basically, if you look at most vapor compression or absorption systems, they're not very good at maintaining humidity. And if you look at this chart, tells us if we should keep the humidity range in the 40 to 60% range if we want to avoid these various bad things, bacteria, viruses, respiratory, things like this. So in many countries, what people do is they cool, and you walk into a space, it's cold, and basically the reason they're doing that is to dehumidify the air, and they're really overcooling it, causing many problems. So if you look at the two systems we'll be comparing, is one, the vapor compression system, which is the 1, 3, 4, 5, and the 4 or 5 many times is not done. The reheat, unless it's a bypass system, can be very efficient if we're actually using heat to do that, and actually is illegal in many places in the United States and throughout the world. Or we can look at the adsorption system, which is the 1, 2, 5, where we have to have some kind of heat sink, and usually that's used as either outdoor air, evaporatively cooled, or it can just be plainly cooled, or it can be indirectly evaporatively cooled to get to the state 5. So we'll be looking at the green cycle here and looking at some effects of various parameters on that cycle and look at what are some of the new developments. So if you look at where desiccants can be applied, you can see many of the manufacturing processes, electronics, beyond buildings, semiconductor, printing, pharmacy, pharmaceuticals is very important, having dry air when they make or tablet-size products for production, fibers, confectionery, and in storage. Artifacts, books, documents, they have to be kept in a certain relative humidity and temperature range, so many times these systems are used, and you can see the various regions on the 2 psychometric charts that you see here. So beyond building comfort cooling or comfort air conditioning, desiccants are used in many other industries. If we can try to classify the industries that we're looking at, first let's look at 2 different types of desiccant rotors. The one on the right, the hexagonal cell rotor, is now no longer manufactured. That manufacturer was using that technology. Most of the rotors you'll see will be corrugated channels. Some will be wound, as you see here, wound from the central hub. Some are actually laid flat and then cut into pieces and fit into a wheel or made into a round wheel. Or some are actually, if they're very large wheels, they will cut them into those pie-shaped sections to fill a wheel up to very, very large diameters. So if we look at this, basically, if we look at the channel size, we're playing a game here. We want to make the channel size small as possible, and I apologize because most of the people that work in this area are in the United States and they usually use English units. So basically, the smaller we make the channel size in mils or thousandths of an inch, we get higher heat transfer rates. So we try to get smaller channel sizes. However, with these systems, you have to be careful with dust and dust accumulation. So that's why you'll always mostly see them operating in a counterflow mode, because that will essentially keep them clean. Or some people have developed systems that actually can be washed down with water that don't deteriorate with the additional of liquid water to their surfaces. But that's a different topic, not the topic of this conversation. So if you look at the various different type of solid desiccant systems that are out there, there are fixed bed systems. Those are mostly used in the chemical processing industry for separation processes. But in the building systems or in the other systems I showed in the previous charts, they're usually rotary systems. The rotor is manufactured, then they put it into a cassette, and they can be used in both residential and commercial systems. Really, the largest wheel that you'll ever see out there is about 16 feet in diameter. The reason why that's really a limitation on how big you can make it, about a little bit taller than this room, is that if you have 2 airflows on either side, if you don't balance the pressure, you have tremendous torque problems on one side of the wheel versus the other side, just due to the pressure differential between those 2 sides. The other big issue is whenever you have a rotating wheel is the seal. So a lot of work has gone into sealing the wheel from one side to the other, so there's no leakage of air from the air stream they're trying to dehumidify to the stream that you're actually using to regenerate the wheel and remove water off the wheel to prepare it for the next cycle. Typical depths are about 200 millimeters. Roughly, sometimes the cost in US dollars is about 50 cents a CFM. And many times, people try to make about 75% of that rotor being actually active sorbent, in other words, active desiccant, either deposited onto a matrix or in situ formed on a matrix. Generally, the maximum uptake of the desiccant, in other words, how much water can it pick up per how many kilograms of water per kilogram of rotor substrate, is anywhere between 0.3 to 0.35, and as you'll see at the end of this section, that's really one of the new research areas, is trying to up that to maybe up to 1 or thereabouts. So therefore, this is one of the areas that people are actively looking at. So if you look at some of the things that can be some typical ranges, I'll define the isotherm shape factor. It goes for anywhere from 1 to 10. The uptake, as I said, we'll look at anyone from 0.1 to 0.3. And the heat absorption is really how much heat is evolved by the sorbent when water is absorbed. That can go anywhere from the latent heat of vaporization, which means the ratio of the heat absorption to the latent heat is 1, up to a very strong adsorbent, which can be up to 3. The rotor manufacturing, there's been variations on how much a rotor could weigh. If you look at a physical honeycomb matrix, the rotor densities have gone anywhere from 5 to 20 pounds per cubic foot. And people always thought, well, is that a big difference? Does that change the performance? Well, I'll show a little bit of that, something about that. We'll look a little bit about rotor depth. The diameter already specified, and the heat transfer we won't cover, but I'll just mention some things there. If you look at a rotor, if you ever go to the ASHRAE show that's in the United States, you'll walk up to a booth and you'll see rotors either divided by 90 degrees, in other words, 90 degrees of the rotor will be used for regeneration, or it could be up to 180 degrees for regeneration. After this talk, I hope you'll understand as soon as you see it, you'll understand, 1, what is the rotor made of, and 2, where it's going to be used. It's real easy to do that, and I'll discuss that in a minute. Generally, the face velocity, we like to keep the pressure drop or the parasitic power low, so we like to keep it anywhere from 200 to 800 feet per minute. Well, it really depends on how much dehumidification you want to have and how much pressure drop and parasitic power. Generally, the regeneration temperature can be anywhere from low temperature, so many times these cycles are used for bottoming cycles. In other words, waste heat out of combined heat and power systems, where the waste heat off an engine can be easily used to regenerate this type of wheel and provide dehumidification. And finally, there's something I won't show in a figure, but is a purge angle, because many times you want to take the combustion products that are on the combustion side, if you are burning a fuel or something like that, or if you have humid air, and purge it around so it doesn't get into the process side to degrade the performance. And that's usually between 5 and 10 degrees, depending on the manufacturer. So if we look at where has desiccants been in really the commercial market, many times in the refrigeration process and process applications when we need very, very dry air, less than 45% relative humidity. Many times conventional air conditioning is either too expensive or can't make that very, very low dew point or frost points required. Now, in some applications you need actually frost points below 0 degrees C, so desiccant rotors are very applicable to that. On the other side, in the commercial market, indoor air quality regulations. In other words, if we have to bring in outdoor air for ventilation, many times a desiccant system is used as a standalone system to pre-treat that outdoor air to bring it into the space, at least at space neutral humidity conditions or a little bit below. So therefore, we're actually taking humid outside air, pre-treating it, taking the water out, and then introducing it into the space as ventilation air. So therefore, if we look at a desiccant, many times they're always classified in terms of the BET or Brunauer, Emmett, and Teller isotherm shapes, 1, 2, 3, 4, and 5. Many times we'll usually looking at 1 or 3 or 4. 1 is typically a strong absorber. If you read the literature, there has been a lot of discussion about what's called a type 1N modified, which is not quite as strong as an absorber. You'll see a little bit of water on different sorbents, type 4, and type 2 desiccant. You'll see many times for a long time in the distant past. Many rotor manufacturers actually use lithium chloride wheels for an adsorbent, and the problem with lithium chloride is in very humid conditions, the lithium chloride material can, what they call deliquesce, it actually forms a liquid and can migrate in the wheel, and that's where you'll see the vertical line on the one there that says 2 in the corner. Let's see if I can use this. Oh yeah, in the corner here, actually goes beyond very, very high uptake and actually forms a liquid system and actually migrates on the wheel. So lithium chloride has been abandoned in any commercial applications. In some industrial applications, they're only used as a replacement for manufacturers or producers that actually like its performance. But these are the different isotherm shapes. So if we look at the standard desiccant material, you'll see is silica gel. What are we trying to do here? Where we can see it at various temperature levels, the silica gel has different values of its uptake. So therefore, this is one of the most common desiccant materials that are either formed in situ on a rotor or try to be attached to some kind of substrate. If we look at the next chart, this really looks at the some typical or 3 typical adsorbents. First is the silica gel that I showed on the previous chart. The difference here is I've collapsed the x-axis to relative humidity to try to get a comparison versus vapor pressure. And then you'll see molecular sieve, which is a very strong adsorber. So you can think of molecular sieve on that surface, there's probably 1 or 2 layers of molecules, water molecules on that surface. So therefore, it's a very strong absorber. And the one I was mentioning for the type 1M is somewhere in between. Does that make silica gel better than molecular sieve? No. It depends on the application that you're going to be using it for. So therefore, an activated carbon, you can see, is better at higher relative humidities, but it does not have a problem of deliquescing. The problem with activated carbon is it does absorb odors and things like this, so many times it's not employed in a desiccant system if you don't want to have odor carryover from one side to the other, which could be a problem with certain adsorbents. So if we look at what we're trying to do here, basically we are pumping water. So what we're trying to do is in the process condition, we're bringing in air at a certain temperature and relative humidity. I would not putting temperature on this chart. And then in the regeneration condition, we are heating up an airstream to a very, very low relative humidity and getting the water out. So essentially we're taking this material, pumping water in, pumping water out. You can think of it as a water pump. So therefore we are actually adsorbing vapor water onto the surface, and that's on the process air condition. And in the regeneration, we're actually vaporizing the water back into the airstream and getting rid of it. And that will have a performance limitation that I'll discuss in a little bit. So the question is, when we started a while ago looking at this, the questions were always where these questions are raised, and I'd like to at least go through these and answer some of them for you. What's the best adsorbent? I showed you molecular sieve. I spoke about the 1M material. I also spoke about silica gel. So what's the best one? What is the effect on desiccant loading? Or like they said, the shape of the isotherm. What is the best system design? And how to do the best system control? What's the best performance? And of course, when we're all done, we want a rotor that actually is not very expensive or have very exotic materials. So this was a fundamental study that we began. So basically, we took an idea that we formed some isotherms. You see here, these are isotherm shapes. The shape factor R comes out of Perry's Chemical Engineering Handbook. So the linear isotherm, R equal to 1, is the silica gel. R of 0.1 is really not molecular sieve. That's sort of the modified molecular sieve, or what I call the type 1M. And then you can see the R equal 2, or we can actually go R equal 10. That's something like the activated carbon. So what is the performance of this? And we basically standardize with an uptake of the rotor of 20% water vapor per kilogram, 20.2 kilograms of water per kilogram of substrate. Now, if we look at these materials, you can't see that on the other chart, and I won't go back. Maybe I can go back. Yes, I can. If I would take these curves and then plot them at, this would be all these assume at 25 degrees C. If I would plot them at higher temperatures, let's say I took silica gel at 75 degrees C, the curve would be a little bit below the silica gel. And likewise, the molecular sieve, 25 versus 75 degrees C, there'll be a curve a little bit below. That difference in shape is how strongly the adsorbent wants to pick up the water. And that's illustrated here. So that first layer of water that goes down onto the surface actually is very strongly adsorbed, so the heat evolved is much larger than the latent heat. And you can see in the case of the molecular sieve, it can be up to 1.8 times the value of the latent heat of vaporization. So there's a lot more heat generated than just the phase change. In fact, some people say that adsorbed water on the surface of a molecular sieve or silica gel is almost like that of a solid water, like ice. The molecules are so closely packed. However, what we do see due to the isotherm shape, molecular sieve does have a higher heat of absorption than silica gel, and this is something that when you do this type of simulation and modeling and experiments, you have to take that into account. So this is a classical recirculation desiccant system. You'll see I have my condition space on the right, and then I have the DW, that's referred to the desiccant wheel, and then I have a heat exchanger wheel, which is HW, so you'll see going from bringing it from the room, that's why it's recirculation. It's first adsorbed and dried, so stream 1 will be hot, and I'll talk about this a little bit later. So we want to cool it down through this wheel tube. Many times in the system, this is not included. We don't evaporate cool back into the air, we just bring it in dry and cooler. And then we take outdoor air, evaporate cool it, and provide the sink for this side, and then regenerate it. And this shows actually a stage regeneration where we can, this is one of the options of doing systems. You heat up the last portion of the wheel so you get effective regeneration and you don't have to heat up the entire wheel using some heat source. It can be either waste heat, a fuel, and that will depend. So if we look at what does the rotor really look like, so we have our two airstreams. We have our process airstream, we have our regeneration airstream. The process airstream is on the top, and the regeneration airstream is on the bottom. So therefore we have these two streams, and basically if we analyze it, it's basically flow in a channel, periodic flow in a channel. So it runs for a certain way in one direction and it goes in the other direction. I won't spend a lot of time, but the equations are pretty well known. Y is humidity ratio. So we have mass conservation in the airstream, energy conservation in the airstream. So you can see the energy conservation has one term, which is the first term after the equal sign. That is the heat that is generated from the absorption process, or it's actually the moisture moving out of the airstream. We have mass conservation in the matrix, how much is absorbed by the matrix. Then we have energy conservation in the matrix. And then finally, the last one is our equilibrium equation. So that's where we put in different materials and see how does the system perform. Okay? So therefore, what we did is first, before we did anything, we got a core sample off of a well-known desiccant wheel. This one happens to be a Sempozyum wheel. And we actually put into a single blow experiment and verified the experiments were modeling the theoretical predictions that we were having. So if we look at also, we actually took that same system and made it into a periodic system, so then we were able to actually simulate both adsorption and desorption periodically using that matrix, and that was also used to verify the numerical condition. And it was a little difficult because of getting the step change in temperature with any fixed bed system is not an easy task, but we had developed and built such a system at the University of Illinois. So if we look at this is a simulation, and this is really to look at system control. So you'll see, I'll talk a little bit about control because eventually these systems have to be controlled. So if you look at the diagram on the right, let me just explain a little bit there. You look at the x-axis is a z over NTU, so this is the beginning of the wheel, that's the end of the wheel, that's why it goes from 0 to 1. And this is at different angles. This is the humidity ratio in the airstream at different angles. So what do you see is that at the first angle, what goes in is equal to what comes out, that's expected, then it dries, but then at the end, what goes in comes out. So this wheel is already saturated, okay? If you look at the wheel on the right, you see it comes in at 0, and then as it goes through, it's still at 180, it's still coming out dry. So what do we know from this system? The wheel on the left is rotating too slow. The wheel on the right is rotating too fast. Now, if we take that, there has to be an optimum in between, and this is this thing, so this curve, so therefore we have designed it, we're controlling it, so just at 180 is where the outlet humidity conditions just start to come up, okay? So we want to contain the heat and mass transfer wave in the wheel. That's how you get the best performance out of these devices. So we look at this, we can see this is our 90-degree 180-degree wheel regenerated at a high temperature. This is like 250 degrees Fahrenheit. So if we look at that, we can see the prediction. The yellow line is the temperature. Look at the purple line, that's the humidity ratio. So you can see the wheel has to cool down first. So that's why we have that little, usually have that little purge angle in there to get rid of this piece. And then it comes up like that. And then we regenerate, and it's just starting to break through the wheel at 90 degrees. So that's why high temperature wheel is 90 degrees. If we look at the same wheel and now make it 180, 180, as you see in this diagram, still with the 250-degree regeneration temperature, you'll see what happens is that we get somewhat similar to the adsorption performance, but what happens is the desorption stops at about 270. So we're blowing out of the system all this high temperatures. So obviously, this is either too high a temperature or not the right desiccant material for this wheel that's split 180 and 180. So whenever you see a wheel that's 180, it's usually low temperature regeneration and usually silica gel. A 90 to 70 degree wheel will be high temperature and generally a type 1 material. Let me look at some selected design results, and I sort of apologize here because in the United States where most of these things are being implemented, the desiccant manufacturers and the implementers use the term grains for its grains of water per pound of water. So whatever you see here, you multiply the humidity ratio axis by 7,000, as we see in the ASHRAE handbook, and that'll get you your kilograms per kilogram of dry air. So I just put that up there. So this is the process we're looking at. So if we look at it, what happens is as we increase the face velocity in the wheel, we actually will get lower difference in humidity ratio. Okay, so in other words, if I want very dry air, I will want slow airflow. Okay, dry air equals slow airflow. If we look at the next diagram, if I have face velocity here, if I look at the drying capacity, even though I have lower delta humidity, as the airflow increases, I will actually get more water removed from the air as the velocity increases. So this is a trade-off. Do I want dry air or do I want more capacity in the device? If we look at here, the heat absorption is always a killer. In other words, the higher the heat absorption, the less we can get the humidity, because what happens is when the material heats up, it doesn't want to absorb as much water, so therefore we always try to keep the heat absorption or have a material that doesn't have an excessive heat absorption. That's why you'll see the pure molecular sieve material is usually not implemented. And the x-axis here is the heat absorption -1, so of course this 0 is equal to the latent heat. Now if you look at it, remember I said back at the beginning, we have a rotor that's either 5 pounds per cubic foot if I weighed it, or I had a rotor that's 20 pounds per cubic foot. Is one better than the other? The answer is really no. The answer is really depends how you operate. So if I have a rotor that's 20 pounds per cubic foot, I'll usually operate around 12 revolutions per hour. That's how fast these rotors typically go. And that's what you'll see mostly. Most of the rotors are at rotating at 10 to 20 or 12, 15 revolutions per hour. The rotor that I showed you that was no longer made was at 5 pounds per cubic foot, so to get the optimum, you have to rotate that faster. That is somewhat of a problem because what you're doing, remember every channel there as it moves around very fast actually captures some air and does bring it in, so the lighter weight rotors do have higher carryover. But from the standpoint of dehumidification, they don't really change. There can be an argument maybe the 5 pounds per cubic foot rotor will degrade over time faster because there's less material there, less absorbent than the 20 pound per cubic foot rotor, but no one's ever really documented that. If we look at the effective isotherm shape, that's what I was saying before, you'll see the linear isotherm has one, this is our silica gel is the yellow, has a given value, but if you want deep drying, that's why you always go to the stronger adsorbent. So in other words, deeper drying, stronger adsorbent, or higher temperature, stronger adsorbent.